So here we are for section 3. This is our last video on new material, so that is pretty exciting. We're still going to be comparing averages, but we're going to look specifically at paired data. Paired data is when you do like an experiment and you want to know if what you do is you have like a matched pairs design. So maybe you want to know if having a protein shake before or after a workout, which way is more sufficient type of thing. So you send the patient to their treatment or their subjects to the treatment to where they're doing the protein shake before workout for 2 weeks, and then back through the process where they're taking the protein shake after the workout. Or you've matched them to someone of similar physique and workout style, and one person does the protein shake before and the other one does it after, and you're looking at the difference. So that's going to be the key word here for this section, is difference. So you'll see a lot of DIFF, diff. So we're wanting to do all the same things that we've been doing. We want to look at the distribution, talk about those four characteristics: shape, center, spread, and outliers, confidence intervals, significance test, and when is it appropriate to use paired T procedures versus 2 sample. So when it's paired, it becomes a 1 sample T situation, versus when it's not paired, then we have 2 complete different samples. So here a researcher studied a random sample of identical twins who had been separated and adopted at birth. Twin A was adopted by a high-income family, twin B, low-income family, and they have IQ tests. So we're looking at the difference of IQ scores. So here's the 12 pairs and twin A's IQ versus twin B's IQ, and then you have a dot plot. So looking at this dot plot, we're looking, there's probably a difference here. So twins raised in high-income households have a higher mean versus the lower income family, and also the standard deviation is higher based on the data that's given right here. But there's a lot of overlap between the groups. So this difference that we're finding with the mean and standard deviation, is it statistically significant, is really the question. So you look at the mean difference. So you have those averages and you subtract, right? Again, with standard deviation, remember, you can't straight up subtract these values. You have to square them, add them together, and take the square root, just like you did before. So here's our new distribution. So the proper method of analysis depends on how data are produced. So this is paired data, so we want to look at the difference of each paired. So we're looking at X bar diff or S diff as our summary statistics. Alright, so another example here. Does music help or hinder performance in math? So researchers Abigail, Carolyn, and Leah designed an experiment using 30 student volunteers to find out. Each subject completed a 50-question single-digit arithmetic test with and without music playing. For each subject, the order of the music and no music treatments was randomly assigned, and the time to complete the test in seconds was recorded for each treatment. Here's the data. So student 1 took them 83 seconds with music, 70 seconds without music. So these subjects were not paired to a person similar to them. They did both treatments. So then you see there's the difference, music minus without music. So it is this line of data that we're actually interested in, that we will be analyzing. So make a dot plot of the difference. Here's our dot plot. Part B was describe what the graph reveals about whether music helps or hinders math performance. Well, you can see there's values above 0 and below 0, and 0 is still included. So there's a possibility that there is no difference. calculate the mean difference in the standard deviation. So, X bar diff, that means music minus without, so you got to make sure your subtraction is in the correct order. And then your standard deviation, remember you're having to add their variances. So what was it? Music squared and then without squared. Add them together and take the square root. Okay, so the time it took these 30 students to complete their arithmetic quiz with music was 2.8 seconds longer on average than the time it took without the music. All right, so actually analyzing the data. There are two ways that a statistical study involving a single quantitative variable can yield paired data. They record two values for each individual, or you match them up into paired individuals. Okay, so the music situation was two values, and then the twins' IQ scores was paired individuals. It is also possible to carry out a matched pairs experiment using method 2. If the researcher forms pairs of similar subjects and randomly assigns each treatment to exactly one member. That's what we were doing in the previous section. All right, so confidence intervals. Everything is the same. You got to check your 10% rule, your sample is greater than 30, everything like that. But it's all based on the difference data. That's the only difference, with the lack of a better word, in this section. Confidence interval formula, same thing. You're looking at the difference of the statistic, the standard deviation of the difference, and the sample size difference. T does not change. You do have here difference, your sample size minus 1. It's actually the same thing because the sample sizes have to be the same. All right, so here's the information again on the twins. So the data, construct and interpret a 95% confidence interval for the true mean confidence interval. So 95% confidence interval, or mean diff, where mean diff is, and you define what the difference is. This is a one sample t interval for the difference. So it's not two samples, it is one sample because it's matched pairs. They were randomly assigned into their column treatments, but the household they were raised in. And we can assume that 12 identical twins, 12 pairs of identical twins is less than 10% of all identical twins raised in separate households. So 12 is quite small, so we graph the data. Again, data being the difference. And nothing crazy skewed and definitely no outliers, so we're good to go. So X bar diff, standard deviation diff, sample size diff. Plug everything into your formula just like before. 3.336 to 8.330. So our conclusion is we are 95% confident that the interval from 3.336 to 8.330 captures the true mean difference, high income to low income, and IQ scores among pairs of identical twins raised in separate households. So from this interval, we're saying that those in the higher income households have a higher IQ. All right, so significance test, same thing. You're looking at the mean diff value, okay? And again, it's going to be 0. Same exact things as before. Nothing has changed, really. Same thing that we're talking about with the difference. You're looking at two pieces of information, but subtracting them to get one piece. Okay, so here we're talking about caffeine withdrawal. So they recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo. The order in which subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table displays data on a subject's depression scores. All right. So you have the subject, you have depression with caffeine, and depression with the placebo. Okay. So we're saying that there is no difference. We want to hopefully find that the difference is actually greater than 0. Okay. The true mean difference in depression test scores for subjects like these. There's no significance level given, so remember by default, we do 5%, 0.05. Okay. It is a paired t-test because each person did both parts. They had the caffeine pill and they also had the placebo pill. Graphed the data, the change, placebo minus caffeine. So in this data set, we do not have the difference column, so you're going to need, or row, you would need to find that information to then provide the graph. Okay, so once you have that difference data, then you can find all the necessary summary statistics to then find your t-value, your degrees of freedom, and then your p-value. So because the p-value is less than alpha, we reject. We have convincing evidence that the caffeine withdrawal increases depression test score on average for subjects like the ones in this experiment. So when is it paired data or when is it 2 samples? So 2 sample T procedure require that data come from independent random samples from 2 populations of interest or from 2 groups of a randomized experiment. Paired T procedures required paired data that come from 1 random sample or from a randomized experiment. Again, when you're looking at paired, you're asking yourself, did they match a person to do both treatments? Did they match a person to another and they each did one part of the treatment and then you find the difference? Versus a 2 sample is there are just 2 groups. Each group did the thing, and then you're comparing the 2. So it all depends on how the data were produced. So we're going to determine if it's a paired or 2 samples. So before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertised a new style of fins that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins, on average. 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or vice versa. The time to remove each type of fin is recorded. So right here it said each diver is going to end up wearing the new fin and the old fin. So this person is going through both treatments. So this would be you're paired to yourself. Okay? You have data from 2 measurements, 2 pieces of information that came from the same person, same variable. To study the health of aquatic life, scientists gathered a random sample of 60 white piranha fish from a tributary in the Amazon River during 1 year. The average length of these fish was compared to a random sample of 82 white piranha from the same tributary a decade ago. Well, these are 2 different samples because one was from a year ago and one's a decade ago. 2 completely different year times, and you're just going to compare the 60 to the 82. Can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. To test this idea, she fills 2 identical drums with bait and covers one in the standard black neoprene wetsuit and the other in the new suit. Over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit. The other 8 are assigned to the drum with the new suit. During each time period, the appropriate drum is submerged in waters that sharks frequent, and the number of times a shark bites the drum is recorded. So this is going to be a 2 sample because you have 2 different groups. You have the 8 time periods with the black suit and the 8 time periods with the new suit. It's not matched up. So again, this section is pretty much the same as section 2. It's just we actually are going to combine the two sets of data into one called the difference and do a one sample t-test, what we call as matched pairs. And on these problems, you need to write that it's a paired t-test, not a one sample t-test.